All right. Hey everyone, it's Matt. I want to take some time today to talk a little bit about point estimation. This is first on our list of inferential statistics activities, and we'll also talk a little bit about confidence intervals, a similar and related idea. So for point estimation here, this is coming because we'd like to approximate maybe a single value. So some sort of population parameter that we're interested in. Recall we may have population and then the smaller sample of the population. We would like to maybe use some of our statistics that are coming from the sample, maybe something like X bar, the mean, the median, maybe the standard deviation, in order to give us an idea. We'd like to approximate the total value for the whole population, so something like mu or sigma. In general, we will use maybe theta and theta hat to refer to population and sample statistics respectively. And for things that we don't have a name for, so mean of sample we call X bar. But if we didn't have a name for that, we could call that mu hat. So we'll use hat for samples here. Now, all of these different estimators in the theta hat table, these are all random variables, and they're coming from random samples. So since we've chosen this sample as only a part of the population, we're not expecting theta hat to be exactly theta. We're expecting some kind of error there. The goal for us will be to use the best possible approximation, the best possible estimate that we can for a given population statistic. So for example, it turns out, you will probably guess this, but you might not know, strictly speaking, you don't know this off the bat. It turns out that X bar, the average of the sample, is the best possible point estimate for the population mean, mu. This turns out to be true. It could have been something else though, we're not exactly sure. We'll see standard deviation may look a little bit different later. Now, confidence interval, what is the point of this? Well, your point estimate is only useful if you're somewhat confident in it. So you can't just say, oh, I think the true mean is close to the sample mean. Well, what do you mean by close? What range do you expect the true mean to fall in? So this is the idea of the confidence interval here. Of course, the size of your sample is going to be pretty important for us in terms of how confident we are. So a confidence interval is a range of values that's likely to contain the true value. We'd like to capture the true value of the population parameter. We often express this as a probability, and it's often written 1 minus alpha. So 1 minus alpha could be 90%, 1 minus alpha could be 95%. This is the probability that our interval captures the true parameter. Some common choices down here, these are pretty common to see. You may have 90% confidence intervals or 95% confidence intervals. I think that's a little more common. But they're often written in terms of the converse, so to speak, or the complement, in terms of alpha either being 0.1 or alpha being 0.5 here. Now, if we think back to the central limit theorem, we know that as long as our sample is large enough, the sample means tend to be normally distributed. So in that case, the sample means have a normal distribution. This is good. This allows us to use our knowledge of the normal curve itself, shown here. So for example, on this nice normal curve here, we may wish to use this standard value of alpha equals 0.05, or written another way, a 95 degree of confidence, 95%. We may decide that's the confidence we are willing to accept. So the idea is that we want our interval, or our range, to consist of 95% inside our range, with these regions outside constituting the other 5%. Since there's two tails, the two 5% get split in half, so we have 2.5% coming over here, and we have 2.5% coming over here. So that's going through for this particular example. In general, for any given alpha, you'd have alpha over 2 be on the right and alpha over 2 be on the left. We often will use this notation here, z alpha over 2. So this is the z statistic that corresponds to this range that we draw here. That's kind of our cutoff. So this is called critical value. So this z alpha over 2 here is the positive z value. We take the positive by convention. That's at this boundary here that separates this area of alpha over 2 from the rest. The corresponding negative z alpha over 2 is on the other side exactly symmetric. In general, a critical value is the number that separates the statistics that are likely to occur from those that are unlikely to occur given a particular tolerance. We state this definition of critical value in general now, because we'll go on to use it later with things other than z. We'll use it for t values in particular. Now, for us here, this z alpha over 2, this is a z score that's going to split up our distribution in this way. And so we've seen before how you can get these particular z scores. So with that, let's go ahead and think about confidence intervals. We're going to be relying on the z score here. Now, we think about having some sample data that's used to estimate population mean. It's going to be subject to some sampling error. We don't expect the two to be exactly the same. Let's call this error E. That's the letter we typically use. This error here is the difference between the observed sample mean and the true mean, subject to some degree of confidence, represented by 1 minus alpha. So this E here, often called the sampling error, so that's the difference between our sample mean, our approximation, from the true mean. So we don't expect those to be the same. I'm going to say population mean here, but in general this is for any statistic. You could define the similar thing. And so we can find the E here using this formula that's going to involve the z alpha over 2, standard deviation, and the size of the population. Recall that's going to come in as well. So this z alpha over 2, that's the critical z value. Critical z value that we've seen already. And we have here coming is sigma x bar. Together, the sigma over square root n, we know from the central limit theorem, is the standard deviation of the sampling distribution. So it'll involve sigma, the standard deviation of the total population, and n, the size of the sample. In general, when we want to write our bounds on our mu, we'll use the formula in this box here. So you'll often see a range given in this way where you'll have x bar minus e and x bar plus e are sandwiching the mu, the true mean, where e is as we've defined. There's a few ways to represent this. You might see it using inequalities. You might see it using plus or minus. So you might say we think the true mean is x bar plus or minus this e. Or it may come in this interval notation. Now, depending on your previous experience, you may be using this a lot. You may not have used interval notation so much. I might say this is pretty common. But the idea is that it's just the range that goes x bar minus e all the way up to x bar plus e, including everything in the middle. So let's go ahead and do an example with this. So let's suppose we're interested in the temperature CPU reaches after a minute from system start. Perhaps we know from a previous study the standard deviation for the machines we're using. And let's say for us, we do an experiment and we repeat it 106 times. So we do the experiment 106 times, that's our n. Maybe after we've done the experiment, we take the mean of everything in our sample and we get this value here, 98.20 degrees Fahrenheit. And happily, we know the standard deviation of our population coming from some sort of previous work is 0.62 degrees Fahrenheit. We are tasked to use the sample data to try and construct a 95% confidence interval for mu. So we're using our sample to try and tell us something about the whole population mu. So that gives us an alpha of 0.05. So let's go ahead and try and find our e. So we'd like to write the mu as x plus or minus e, where our error is given using the z alpha over 2, sigma, and root n. Now we have sigma. Happily, we have n. It was our experiment. We know how many in the sample there are. We need to find this z alpha over 2. So let's think about how we might find that. So you might write this as z of 0.025. The idea being that we have some kind of normal curve here, and we'd like to isolate after z over 2 this little bit out here where there's just 2.5% over here. So we'd like to find this z alpha. We are using the empirical rule, kind of expecting this to be around z equals 2. We expect 2 standard deviations from the mean to section off about 95% of the data. But let's do this exactly. We can do this in R. So from R, let's think about the 97.5th percentile. We can use this using the function we learned previously. We can, since we have a percentile and we'd like to go back and find the z score, this is not p norm, but the opposite. We'll use q norm here with the given percentile. And this is the standard normal curve that we're applying it to, so we can supply 0 mean and 1 standard deviation. If you leave those 0 and 1 off, it will be the same. Those are actually the default value. You can compute this in R, and as we expected, you get pretty close to 2. It's about 1.959964. This number, this 1.96, is a number that you see quoted often. Many people will have this in their mind. So if we're trying to find the confidence interval, we can do so We'll need to compute E by subbing in these values. So we have now all three of them, so let's put them in. Standard deviation and the square root of 106. One can crunch that out. It comes out to about 0.1180. And so now all of these numbers come together to give us our E. And so we can compute now the 95% confidence interval. Often we will abbreviate confidence interval to just CI. Feel free to do that. So this can be written in many ways. So we were writing it with plus or minus earlier. We can write it using the inequalities down here. So this is the general form. Typically you would compute this out. So you can take the sample mean minus this computed value for E, and the sample mean plus the computed value for E. And let's, just to get all of them, write this in the final way using interval notation. So you compute those numbers out, and you'll get about 98.082 all the way to 98.3108. That's in degrees Fahrenheit. So we found a range. So this is the 95% confidence interval. We're expecting this range to capture the true mean. So the true mean mu exists. It is somewhere. And we think with 95% confidence that this range that we've established does contain this mu. So that's how we can interpret this result here. In part B, we're being asked to repeat this only using now 95% confidence. So you can think to yourself, how is this going to impact the size of our interval? If our confidence is going to go up, if we're going to become more confident that our interval contains the true mean, this should give for us now a larger interval. So we're expecting our interval to get wider or larger to give us this additional confidence. Let's compute it out and see what we get. So this is a similar problem. Here we now have a different alpha. So we've got alpha equals 0.01. So we will have to again compute the critical Z statistic here. We'd like 0.005 on each side. So let's find the Z value that has 0.005 to the right of it. Or in other words, we want to have 0.995 to the left. We can again use our familiar Q-norm function to compute this. In this way, we can find Z of 0.005. This time, let's just supply the value. It defaults to the standard normal distribution. And this comes out to be a bit bigger, 2.57. This is what we expect. We're making this interval larger. Our new Z is now farther to the right. With this in hand, we can go ahead and find our E using our similar formula from before. Square root 106. And the value we get here is about 0.155. Let's take a look at the one previously. That was about 0.118. This is 0.155. So this one is definitely bigger, and so our confidence interval is going to be wider. So we have now the 99% confidence interval. We can compute by taking our mean x bar, sample mean, and adding and subtracting this. Let's do that here. Let's subtract 551 and let's add 0.1551. Let's put that together in an interval. So this is coming from x bar minus e and x bar plus e. You can crunch that out, get about 98.05 degrees Fahrenheit all the way to 98.36 degrees Fahrenheit. We can notice again from before, we had 98.08 was our lower range before. It's now wider, 98.05 versus 98.31 before. We have 98.36 now. So we should take a second to notice this is wider. That's what we were expecting. So this is wider than for the 95% confidence interval, as we were expecting. Good. Okay, let's keep moving on here. So far the problem that we've done is to think about a sample that we've already collected and try and find the interval. However, when you're designing a study and conducting your own experiments, you have control over the size. So there is this question of what size sample do we need? We could take bigger sample, we could take smaller sample, and then look at the corresponding E. So if there's an E that you desire for some reason, you can then, by basically doing this computation we've done backwards, figure out what sample size you need. So let's go ahead and try that. So let's start with our familiar formula for the standard error E. But let's suppose the problem is a little different. Suppose we have a fixed level of confidence. Let's suppose we have a fixed level of confidence. We normally have that. That's 1 minus alpha. And we know the standard deviation. That's also fixed. So that's sigma. So if we know sigma, we know z bar. Let's think about us having a target for E. Let's think about if we knew E up front, or we had in mind what it should be. Let's try now to solve for n. So we can take this equation and rearrange. Let us first clear the fraction. And then get rid of the E. In this way we can solve for n. Let's take square of both sides. In this way, if you have E as well as sigma and z alpha over 2, you can combine them in this way to find the sample size that you need. Now, this will often give you some kind of decimal answer. You may find that you need 35.3 people to be in your study. You should always round up. Not only are you not going to be able to find 0.3 of a person, but if you take anything lower than this value, you won't have your desired E. So let's take a minute to play with that by means of example. So let's imagine thinking about maybe the mean age of computers. Here is a very old computer pictured. So let's say that at the onset, we're deciding that we want 96 degree of confidence. So that will give us our 1 minus alpha. In other words, alpha is going to be 0.04, a little smaller than usual. We have from a previous study the standard deviation, sigma. It's apparently half a year. And we are also specifying here that we would like the sample mean to be an error of no more than 0.25 years. So that will give us our E. So imagine you're trying to estimate the mean age of computers, and you know before you do the study that you're going to accept an error up to a quarter of a year. Then you can determine for yourself how many N you're going to need to go out and sample in order to achieve this E. One thing we do need to compute here is we need to find, given our alpha, we need to find Z alpha over 2, or Z of 0.02. We can do that, of course, using Q norm. Let's supply 98 in here, and that gives us about 2.05. We can now combine everything together. In our formula for N, we have Z alpha over 2, we have that. Sigma, happily, we have that. And the E is given, it is imposed on us. All of these numbers we can crunch in here. Standard deviation, our desired E, and we'll square the whole thing. At the end of the day, we're achieving something like 16.8. Of course, we should always round up. So if we wanted to do this, we would require a sample of at least 17 computers. Not so bad. If you thought you needed 100, without doing this computation, you might waste a lot of time and valuable resources when 17 is sufficient. So now we're getting a sense of how these different variables are impacting each other. So recall our formula for sampling error. That we had, the E equals Z alpha over 2 sigma over root N. If Z alpha over 2 is increased, so too will E be increased. If the Z value goes up, so does E. Same for standard deviation. If our population is more variable, our E will increase. Our range will not be as tight since we're expecting a lot of variation. Whereas, as we notice, the N is in the denominator. If the N is increasing, our size for E will decrease, and we will tighten up our bound. So the larger our sample is, the smaller our confidence interval will be, and the tighter control we will have over the true population statistic. So that's where we'll leave it now. We'll go on to continue and interpret these things, do a few more examples in class.